Hi, we are Sonia González Telles and María José Chaboya Zamora, and we are going to present our final project, Diffraction to a Hair. This is the outline of our presentation. The objective is to obtain a Fraunhofer diffraction pattern using a hair and analyze it, and the specific goals are to measure the width of a hair by analyzing the diffraction pattern created when the hair is illuminated with a monochromatic source of light, and also to obtain the experimental value of the wavelength of a light source.
To start with the introduction, we must first define diffraction. Diffraction is the process of light bending around an obstacle or spreading out after it moves through a small space. To understand this phenomenon better, we can study Huygens' Fresnel principle, which states that each point of a wavefront is a source of a secondary waves, and the amplitude of the resultant field at some point can be obtained by analyzing the superpositions of waves, as we can see in the first figure. But now, depending on where we place the observation screen, we will observe different types of diffraction patterns. However, we are only interested in Fraunhofer or far-field diffraction for this experiment, which occurs when the diffraction pattern is observed considerably far away from the light source, as we can see an experimental arrangement for Fraunhofer diffraction in the second image.
Now, for this experiment, we could use the diffraction equations for a single slit, this by applying Babinet's principle that states that the irradiance distribution obtained through complementary screens will be the same. Since the single slit has exactly the same transparent regions as the opaque regions from the hair, these screens will be complementary and we can use Babinet's principle. Then for the single slit, we know that the irradiance at a point P on the screen will be given by equation 1. And from this equation, we notice that we will obtain the minimums when this term beta is a multiple of pi. And we will be able to obtain the location of the dark fringes through equation 2. Now, assuming that the angle theta is small, we will be able to relate these terms sin of theta with the distance to the screen and the separation of the minimums.
Now here we have the materials we use for the experiment. Here's the experimental setup that I use for our experiment. We use the red laser, a human hair, measuring tape, and the ruler. And as we can see in the second slide, this is Tanya's experimental setup. She used the same, just a different razor laser and her hair. And here we can see the diffraction pattern and a close-up to the experimental setup. To obtain first the width of hair, we first needed to know the wavelength of the radiation, so we used the CD as a diffraction grating. We used the experimental arrangement as we can see on the figure on the left. The experimental consists of using a CD as a transmission grating, so first we must remove the aluminum coating to help, and to do this we use adhesive tape to remove it, and then we positioned it vertically in front of a monochromatic light source. And in this case we used a red laser, and at the far end of the we place the observation screen or use simply the wall. And when the light passes through the disk, it creates a diffraction pattern as we can see in the figure on the right. And we recorded the distances to obtain the wavelength of the radiation. And for the second part, after obtaining the wavelength of the radiation, we can continue. And we can see the experimental setup is on the left, where the arrangement consists of placing a strand of hair in front of a light source to produce diffraction. To do this, first we had to tape a hair into a cardboard opening to hold it in place, and then we shine the laser beam to the hair, making sure that the cardboard didn't interfere with the laser beam path, and observe the diffraction pattern that was created at the far end of the wall, and recorded the data to obtain the width of hair.
We'll continue with the analysis. First, we are going to start with the wavelength analysis. As Majo said, the CD serves as a diffraction grating, so we can use the diffraction condition for gratings given by equation 4. We recorded, as Majo said, the distance from the disk to the screen and also the distances between the central maximum to the maximums of order 1. And we could find the angle theta given by equation 5. With this angle, we could obtain the wavelength of the radiation, rearranging the diffraction condition, and using that, we only analyze this for the maximum of order 1, and with a width of the grating of 1.5 micrometers. We obtain this data here for the angle theta, for the sinus of theta, and for the wavelength of the radiation. We calculated the average of the wavelengths and obtained for my laser a wavelength of 669 nanometers plus minus 7 nanometers. Continue with the experiment to obtain the width of the hair. We recorded first the distances from the center of the observation screen to the different minimums, and we could also divide the values of the distance from the center of the screen to the minimums by the distance from the hair to the screen, and also by the wavelength of the laser obtained. And we rearrange the diffraction condition, and we, as in equation 7, and we observe that it is possible to plot the minimums, the orders of the minimums, as functions of this quantity in the table above. And it is possible to use a linear approximation with a slope a, that is the width of the hair. Then we obtain the slope 0.0079 with this error, and as we said, this slope will be the width of the hair. In my experiment, I obtained a width of 79 micrometers, plus minus 0.2 micrometers, and the average width of a hair is between 17 and 180 micrometers, so the result is between the ranges, and we conclude it's a good result.
Then we repeated the first both experiments, and analogously to what Sanya did. First, we need to obtain the wavelength of the radiation, and in the table that Sanya is pointing, we present the values of the distance from the center maximum to the first order maximum. And okay, and we, as we previously mentioned, we can apply the diffraction conditions and obtain the angle theta given by equation 8, and we apply the diffraction condition with m equal 1. Then we obtained in the following table the results of the the results of the calculations for theta, sine of theta, and the wavelengths for each of them. After them, we did an average, and we obtained a value of 661 plus minus 3 nanometers, and we obtained this value, which is well within the range of the manufacturer. So we concluded this was a good result, and we calculated the associated errors through error propagation theory in the following equations. And now that we know the wavelength of the radiation, we continue to do it for the to obtain the width of the hair, as Sanya also did. We obtain the values. We presented in the table the values of the distance of the center of the screen to the minimums of order n, and then we divided the values of y by the distance d and the wavelength, as we can see in the second table. And then we plotted the values of the dark fringes m as a function of the second column of the previous table, and we applied a linear adjustment with the help of equation 14, and we obtained the hair width of 71.3 plus minus 0.4 micrometers, which is very well in the average width of human hair, which is 17 to 180 micrometers. And as me and Sanya obtained very similar results, we concluded both were very accurate. And to conclude, in both experiments, we successfully obtained the width of a single human hair by analyzing the Fraunhofer diffraction pattern. In the first experiment, we obtained a value of 79 plus minus 0.2 micrometers, and in the second experiment, we obtained a value of 71.3 plus minus 0.4 micrometers. However, we also obtained the values of the wavelengths of the light sources that we used in the experiments, and we obtained a value of 669 plus minus 7 nanometers in the first experiment, and for the second one, we obtained a value of 661 plus minus 3 nanometers, which are both within inside the ranges given by the manufacturers. And in the following slide, we present the references we used for these experiments. Thank you.